Yeah, on some of them, I felt like the equation didn't make much sense, so I kind of gave like an example.
All right. Let us talk about continuing our 10.3 journey. So we talked about what this vector capital T was. Okay. It was defined as the unit vector to some vector R. And yes, actually, we need to put some primes here. Okay. Then we define our curvature. We defined it as this quantity. Okay. But notice that by the chain rule, we can just say that this is equal to this. When you multiply by reciprocals, the dt's cancel. And this implies that we can now derive a new expression for curvature. So this is an equivalent formulation of curvature. Now, let's use this definition here to prove something about the curvature of the circle. Okay. Indeed, T is this R prime over R prime norm. Okay. So let's prove something about circles here. Prove the curvature kappa of a circle of radius A is 1 over its radius. This is a very interesting result. A very interesting result. So, you know, in R2 at least, and in R3 we can generalize it to R3. Let's say we have a circle centered at the origin of radius A. What equation expresses this mathematically in R2? And R is A, so it's A squared. Okay. Notice that we can parameterize this curve using what parametric equation? Okay. Yeah, sine and cosine. What parameterizes the x coordinate in the unit circle? Yeah, so over here, we want to have this involve a cosine of t. But in the unit circle, the radius of the circle is 1. Here, the radius of the circle is a. So we have to scale this by a. And you'll see why that makes more intuitive sense in a second, because it'll rederive this equation. Similarly, b will be sine of t. And your z component, we could just set it equal to 0. That way, even if we included the fourth dimension, or the third dimension, z, over here, our picture wouldn't change. If we set z equal to 0, that fixes the z value to be equal to 0, and our circle is now no longer in R2 and R3, it would be inside the xy plane, right? Good. Now, notice that this is our x, this is our y. I'll show you why that rederives this. Notice that x squared plus y squared, based off of that, implies that you have a cosine of t cosine squared plus a sine of t cosine squared. This is equal to a squared cosine squared t plus a squared sine squared t. I can factor out the common term a squared. I get cosine squared t plus sine squared t. What is that in the parentheses equivalent to? Very good, by the Pythagorean identity. This inside the parentheses is equal to 1. So this equals a squared. And that's how we even got this relation to begin with. This relation is an implication of parametrizing how the coordinates on a circle in the x component and how the coordinates on a circle in a y component vary based off of the cosine of the angle theta and the sine of the angle theta and the Pythagorean identity. So that's how we get this, okay? And then we want to compute curvature. So here's my argument to you. Would you guys believe that the curvature at 0 is the same thing for the curvature at any t, where for all t an element of the real numbers? Why? Yeah, the curvature should be the same on all the points. All the points are the same, and all the points curve the same, or else it wouldn't be a circle. So the curvature is the same at time equals 0 with the curvature at any time, the quantity, the curvature. So this is the same. So Wu log, we can just show it for k is 0. Wu log. Who here knows what Wu log stands for?
Sounds like Klingon.
Nope. Wu log stands for without loss of generality. Us mathematicians say this all the time because we prove things in general. And if we're going to make an argument like this, we then say, oh, without loss of generality, we can prove it for k of 0 because k of 0 and k of t are always the same. And so it doesn't matter if I just prove it for k of 0. Without Wu log, it works for k of t. Okay? So let's compute curvature here. Notice that to find what curvature is, we need to know what r prime of t is. What's the derivative of cosine?
Negative sine.
The derivative of cosine is negative sine, so this becomes negative a sine of t. What's the derivative of sine?
Cosine.
So this becomes a cosine of t. Did I put b here?
Yes, you did.
This does not need to be a b. Okay. I just think it's alphabet time. A, B, C, D. Nope. Okay. A cosine of t, okay, and then derivative of 0 is 0. Even I know that one. All right. So let's evaluate r prime of 0. Okay, because it suffices to show what k prime of 0 is. So we'll evaluate r prime of 0 and t prime of 0 in a second. What's sine of 0? 0, so negative a times 0 is 0. What's cosine of 0? 1, so 1 times a is a. Well, oh, okay. Now, t prime, okay, let's calculate that here. before we do that, let's discuss what t is and then take the derivative of it. Okay. T would be the normalization or unitization of magnitude of r prime. So r prime is this. What is r prime's magnitude? Yeah. So right? But since we're evaluating for t equals 0, it suffices to find this as well, right? So then I'm plugging in 0 for sine of t, that's 0, square it, 0. 0 for cosine of t, that's 1 times 1, which is times a. Square needs to be here. So when I plug in for 1, cosine of 0 is 1, and 1 times a is a. Square a, you get a squared. Square rooted, you just get a. Okay. So this term is merely just a. This term is this vector. So I'm the same thing as this expression. Okay. So the a distributes to each term, and you get this. This is my t of 0. Okay. Correct? Hmm?
Yeah.
Okay. Thank you for that feedback. Okay, so now that we found that, recall, we want to find this expression to kill off the problem. Okay? Now we know what r prime of 0 is, magnitude. R prime of 0 magnitude is just a. Now we just need to find what that vector t prime evaluated as 0 is. But we know what that vector t is somewhere around here. Right here. So over here, t is equal to t of 0. Do I have it on the board?
Yeah, I think so.
Where is it? Oh, here it is.
And even
Oh,
a
wait.
little bit further up.
Oh, here it is. Yeah. Here it is. So, okay. That's equal to this. Now, I plugged in, so this is t of 0. Okay, what is t of t? That is precisely the derivative right here. Boom. Negative a sine t, a cosine t 0, divided by the norm, or the magnitude of this guy. So negative a sine t quantity squared plus a cosine t quantity squared plus your 0. Notice that this breaks down to, this is much easier. I like this angle. So whenever we square it, it distributes to the a's. We can factor out the a, square root that. Then we get the a over here. And then we get, this is just the square root of sine squared plus cosine squared of t, which is square root of 1. So this just becomes a down in here. Distributing this a to each of these is equivalent to this. Okay, that's our t of t. This is our capital T of t. What is it primed? What is the derivative of that guy?
Negative cosine, negative sine.
Aha! Capital T prime of t. Derivative sine is cosine, and it retains that negative. Derivative sine is cosine. Oh. Derivative of cosine is negative sine. And that is just a 0. Boom. So at the end of the day, I wanted to evaluate it at 0. So let's evaluate this guy at 0. Cosine of 0 is 1, so this becomes a negative 1. Sine of 0 is 0. That is just 0. So this is A. Evaluate it at 0. Wait a second. This needs to have A's in it. What gives? Oh, so see, I fudged up this calculation here. I don't need to be dividing it by A over here. Because we were trying to calculate T prime, we didn't need to divide by A over there. This is just T, okay, of T. And T prime would be its derivative, and those A's have to stay there, okay? Those A's have to stay there, because they're just constants. So this ends up becoming an A. This ends up becoming a negative A sine T, derivative of cosine. Derivative of cosine is negative sine. What's going on? Okay. Derivative sine is cosine. This needs to be cosine. Okay. All right. So then when we do this here, evaluate at 0, we're evaluating that thing at 0. So it's still this. Okay. Okay. So notice that ends up equaling okay, those are just zeros. And when you square negative A, it becomes positive A squared. Square root, it just becomes A. What is going on here? Something went wrong here. Something is off. What? Okay. I can't spot what went wrong here. I'm gonna have to. This is true right here. K of 0. That's true. So let me just do this one more time here. I'm gonna retrace my steps. I don't know where the error is, and I'm out of board space. And I hate it when I don't have room to do stuff. So I'm just gonna start doing it real quick from the top. Our parameterization of the circle is this: A cosine of t, A sine t, 0. Derivative of this, derivative of cosine is negative sine. Derivative of sine is cosine. Okay, so r prime of 0 is this evaluated at 0. So sine, this becomes 0. This becomes A. This becomes 0. Okay, done. Next, the norm here at 0 It's just this thing, A. So we know this, we know this. Okay, so r prime of 0 over magnitude of r prime of 0 is just 0, A, 0, all over A. Okay, this results to 0, 1, 0. Then our t is equal to this. Okay, actually, precisely, it's t of 0. So what we get here, so what we get here is k, which is equal to this. Down here, our norm is at a, and up there, we just need to know what t prime evaluated 0 is. And when we take its magnitude. So our t was, I erased it, but our t was okay. And we've computed that for t of 0. This ratio has been computed, and it's equal to this. So when we norm it and take its derivative, all that occurs is you just take the square root of 0 squared plus 1 squared plus 0 squared. And so this becomes 1 over a. So we're done. That shouldn't have taken this long. It really should not have taken that long. But that shouldn't have taken that long. Okay? So, next, moving on. I sunk too much time into this example, even though it's a very cool result. And it's not that hard. You just gotta compute each of these one at a time here. I tried to compute too many of them at a time, and the board space flustered me. It can be proven that there is another formulation that r prime cross r double prime divided by the magnitude of r prime cubed. This is an equivalent formulation for curvature, but you also gotta put some magnitudes over here. Okay, I will show how this is proved. I have it in my notes, but I'll show this on YouTube. But let's apply that to a situation. Okay, let's apply it to a situation. So find the curvature of this function at the point 0, 0, 0. Okay. So we need to take the derivative of r, second derivative of r, to be able to do this problem. R prime is the derivative of this thing, so it's 1, 2t et squared. And r double prime is the derivative of this thing, and that's 0, 2, 6t. Now we got to compute r prime cross r double prime, and this is equal to the determinant I, j, k, 1, 2, t, 3t squared, 0, 2, 6t. This decomposes to I hat times the 2 by 2 determinant 2t, 3t squared, 2, 6t, minus j hat determinant 2 by 2, 1, 0, 3t squared, 6t, plus k hat 2 by 2 determinant 1, 2t, 0, 2. This breaks apart to I hat times 2t times 6t, which is 12t squared, minus 2 times 3t squared, which is 6t squared, minus j hat times the quantity 1 times 6t, which is 6t, minus 0, plus k hat times the quantity 1 times 2, which is 2, minus 0. Okay? And so this is equal to, over here, we combine like terms. So this becomes a 6t squared I hat minus a 6t j hat plus a 2k hat. And you know I like to express this like this. Okay? So we've computed the cross product of r prime and r double prime. It's this vector. Then to compute curvature, it says, well, you need to take its magnitude. So the magnitude of this thing is equal to the square root of 6t squared, everything squared, plus negative 6t, everything squared, plus your 2 squared. This results in 36t to the fourth plus 36t squared plus your 4. That's what this thing is. So I will create some space here, put this up here. Divided by this r prime cubed. I erased r prime, right? The one thing I needed, I erased. We can compute it real quickly again. Remember, RT was defined to be t squared, t cubed. So r prime of t is 1, 2t, 3t squared. Norm of this, or magnitude of this, is equal to this. 1 squared plus 2t squared plus 3t squared, which is equal to the square root of 1 plus 4t squared plus 9t to the fourth. Square root 1 plus 4t squared plus 9t to the fourth. Okay. But recall, I erased it. The problem says evaluate it at the point 0, 0, 0. That's my x, y, z, an element of R3. Okay. So notice that in the parameterization, x is equal to t, y is equal to t squared, and z is equal to t cubed. But at this value z equals 0, that implies t cubed is equal to 0, which implies t is equal to 0. Okay? So at this point of evaluation, it suffices to find what the curvature is at 0. And upon making that connection, it suffices to find what the function on the left-hand side of that equation is when we replace every t with a 0. Okay? Notice that by the properties of square roots, I can include it in all in one square root. So if that's a 0, everything with t's goes away. If that's a 0, everything with t's goes away. Did you get the square root of 4, which is what? Yes, plus or minus 2 technically. But we'll take the principal square root. But I will note that there is such a thing as positive and negative curvature. So in the study of differential geometry, what are the sum of all the interior angles of a triangle? 180. That is only in a flat Euclidean space. What would be the sum of all the interior angles if I draw the triangle on the surface of a ball? Yes. Oh my goodness. I love being surrounded by nerds. You guys get me. Nerds get me. You guys making me happy. So this is positive curvature. This is curvature that's flat, so it's 0. You can also define negative curvature. The sum of the interior angles here is greater than 180. But what if I draw the triangle on a Pringle? Or a saddle, a horse saddle? You get something that looks like this. Ooh. Some of the interior angles is how much there? It's less than. So it's very cool now. Geometry is much more interesting and complicated than just the flat space geometry we do. And curvature has to talk about this. So we calculated that the curvature of this surface can be actually plus or minus 2 after we're done. So that's a really interesting notion, that it could curve out or it could curve in. That is what the mathematics suggests. So don't forget that taking a square root, plus or minus. Don't forget that. Every even root gives you a plus or minus result, right? Does that make sense to everybody why that's true? That's plus or minus 2? Because both plus and minus 2 satisfy that definition. When you take the square root of 4 and you get a number out of that operation, the square root is a question. It says what number times itself will equal 4? Positive 2 times positive 2 equals 4. But so does negative 2 times negative 2. That also equals 4. So they're both, it's both true. Another theorem that I wish we could prove, I really wish we could prove, but this is not a differential geometry course, it's just a Calc 3 course. I will prove it on YouTube. Is this formulation in terms of f of x. Okay? Curvature can also be defined as that. So let's do a problem having to do with it. Let's compute a curvature value. So let's say we got my f of x, which is my y, which is my x squared. We want to compute what is the curvature at the points 0, 0, 1, 1, and, you know, maybe 2, 4. So that means we got to get our function and take 2 derivatives of it and 1 derivative of it to be able to plug it into this formula. So f prime of x is d dx of x squared, which is what? 2x. F double prime of x is equal to d dx of 2x, which is 2. So we plug it into that formula here. The top is the second derivative, okay? The bottom is 1 plus f prime of x squared to the 3/2 power. Does everybody know what the 3/2 power means? Excellent, yes. Yep. Yep. Okay, so then now we get this is 2 all over 1 plus 4x squared to the 3/2. But we aspire to evaluate it at these points 0, 0, 1, 1, 2, 4. Okay. You could do that. You could do that. But notice that you can also say my function f of x is a function of x. And this, I wrote t because I'm getting used to just writing t. But now, actually, what I neglected to state, the highlight of this formulation of curvature is that you can make it a function of x. Notice that there was no t's in the expression. I shouldn't have put t. I'm only human. I don't sleep that much. I need to, right after this class, I'm going to go home and sleep. I'm just going to hibernate until our test in lab. And wake up soon enough to get here. So actually, what is the x component here? It's 0. So I can just plug in 0 for x. So yeah, you guys don't get a lot of sleep either. So I get that. And I'm sympathetic and empathetic to you. So then this becomes just 1 to the 3/2 power, right? What is that? What's the square root of 1 cubed? It's just 1. This becomes 2. And at 1, 1, x is 1, so we just put this like this. Okay, so that's the same thing as 2 divided by 5 to the 3/2. Make sense? And at 2, 4, you just get this. 2, 4. Okay. So then this becomes 2 all over 1 plus, this is 4 times 4, which is 16. So this becomes 2 over 17 to the 3/2 power. Making sense? It's not that bad. Derivation of that formula is really cool. Derivation of all these formulas is really cool. It's really not that bad. I don't know what the heck that curvature of a circle thing was gotten me weird. It happens, man. It happens even to Terrence Tao. You'll see Terrence Tao having a lecture, and he'll be like, of course, I forgot to do the computation, Terrence Tao is this Australian accent having Chinese dude who's a very good mathematician. You watch his lectures, he messes up too. I'm over here trying to console myself.
I think that comes with the job description of being a mathematician.
Making mistakes? Oh yeah. That's actually how we make all our discoveries, is making mistakes. Then realizing I made a mistake, how do I fix it? And when you fix it, you made a discovery. Now let's talk about normal and binormal vectors. Cal 3 is getting really cool now. Rev that engine, the Cal 3 engine up. It's getting really cool now. There's all kinds of cool stuff being defined right now. Curvature, normal and binormal vectors, what is that? So let's say you got an arbitrary curve in R3. You can define a little patch of surface that contains that curve, right? Just a tiny plane, just a little plane, little patch of surface that contains this point. There's quite a few vectors that we can talk about here. There's our beloved t vector, okay? Remember t? Then, so look, before, let's forget about t. What is r prime? Well, this curve right here is what r of t is. R of t is a vector from the origin that points to each of these locations on the curve at various parameter t value. So what is r prime of t? And what is it when you divide up all of its components by its own magnitude? Well, r prime of t would be like something like that. It's like right on top of t. They're right on top of each other, but r prime of t gets scaled by its own magnitude to become t.
So it's a unit vector.
Unit vector, yes, sir. Now it can get scaled shorter or scaled bigger. It just depends on what it is, you know. But whatever it is, if it's greater than 1, you bring it down to 1. If it's less than 1, you bring it up to 1. So then we can define, oops. Our n of t. Okay? N of t is just a normal vector to your t. I could have had it going that way. It doesn't matter. I just want to stay consistent with this one picture in the book. Okay? Because technically, if I had it going down, everything works out. The signs will kind of change. The cross products value will change. You know, if I take this cross that, then that goes into the page versus that cross this would go into the page. The only thing that would change is the cross product and the sign you would get. So in order to remain consistent with the mathematics of the original derivation, we'll just have it like that. So then the binormal vector, notice that this vector t and this vector n are in a plane. They're flat, they're in a plane. Okay? It's not necessarily the xy plane or the yz plane, but it is a plane. Okay? Then you can create a mutually normal vector to both t and n. That B is called a binormal vector because it's normal to two other vectors. What's an example of a binormal vector? I don't know, k hat. K hat's a binormal vector to I hat and j hat. X hat is a binormal vector to k hat and y hat, right? So we've seen binomial vectors. We just never said this is a thing. We never said this is a thing that we find interesting and we want to talk about. But we define this binomial vector B as, you guessed it, a cross product of these guys. Because how else would you form a vector that's normal to two other vectors? The cross product generates that. The cross product is, take two vectors, I can generate a binomial vector, two of those vectors. Okay. Oh, and we can define n. N has an interesting definition. Remember what t was doing to r prime? N is doing that to t prime. Y'all see that? Very interesting, huh? Very, very interesting. Okay. Notice that t dot t prime, what does this equal? Remember when we were calculating t for the curvature of a circle problem? Remember how t was like a cosine and negative sine and 0? And we took the prime of that, and then we got like negative cosine, negative sine. So taking the derivative of t is actually causing it to rotate by how many degrees from its original starting point? 90 degrees. In my head, I think of it as analogous as, oh, I had both negative components on the cosine and sine. That's as if it was like in the third quadrant in trig, versus one of the components was negative, and that means it's either in the second or fourth. So if it went from second or fourth to the third quadrant, there must have been a rotation by 90 degrees, either clockwise or counterclockwise. Yeah, I like the head nods because you just like, oh yeah, it makes intuitive sense. It's quite the heuristic argument, but it still works. So let's find a B in a concrete example. I need some space here. Let's say that B is equal to cosine of t, sine t. This is the prototypical parameterization. A helix. And we want to know what is B. Recall, B is equal to, n, yeah, t cross n. You got to have the order correct, right? Because cross products don't commute, they anti-commute. Right? You guys familiar with that terminology, commute? Like 3 times 4 and 4 times 3 are the same value. So 3 and 4 commute. t, remember, it equals r prime, r magnitude of r prime, and n equals t prime, all over magnitude of t prime. So first things first, we got to take a derivative of r, and then we can find t, and then we can take the derivative of t, and then find n. Okay, and then once we're done doing that, we can take their cross product. So notice that r prime of t is the derivative of this guy. Derivative of cosine is sine. Derivative of sine is negative cosine. And derivative of t is 1. Derivative of cosine is negative sine. Derivative of sine is cosine. Thank you very much. Okay. Now that we know r prime of t, the magnitude of r prime of t is equal to the square root of negative sine t squared plus cosine t squared plus 1 squared is equal to the square root of 2. Okay, so then this t formulation over here t is going to be equal to r prime divided by its own magnitude, root 2. Okay. So we get what t is. It's this guy. And, you know, I could distribute the square root to each of those components, or I could just keep it like this. There's less things to write if I keep it like this. Now, we want to find n. So we got to take the derivative of this thing. Derivative of sine is what? Cosine. Derivative of cosine is negative sine. Derivative of 1 is 0. It's doing that thing, guys. It's switching quadrants. You see that? Negative cosine, negative sine is usually quadrant 3. Negative sine, positive cosine, usually quadrant 4. So it went from like quadrant 4 to quadrant 3. 90-degree rotation. Therefore, it's going to create a perpendicular vector. Then we need to calculate the magnitude of t prime, which is just the magnitude of this thing. Square root of cosine squared t, sine squared t, plus a 0. Pythagorean identity gives me that this is square root of 1, which is 1.
Oh, don't forget the for t prime when the square root 2 we carried, it's a constant.
Oh yes, 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 yes. You're absolutely correct. So then t prime is just 1 over root 2. We got this over here. We got this over here. We got this over here. And we can calculate it all now. Yes. We're going to have to calculate it later. See you guys at 2.